Hi everyone, I am Oren and I'm glad to present our paper ParallelPARC, a scalable pipeline for generating natural language analogies. This is joint work with my collaborators from the Hebrew University of Jerusalem, Israel. The analogous reasoning process is one of the pinnacles of human cognition. It allows us to abstract information, form flexible concepts, and solve problems based on prior experience. Many researchers have argued that even though these abilities are so crucial, they are still lacking in current AI systems. Analogies play an important role across many areas, such as design, technology, arts, mathematics, law, and education. In fact, many scientific inventions emerged thanks to analogies. Let me give you one cool example. Here is Odon, a car mechanic that has watched a YouTube video demonstrating how to extract a cork that is stuck inside an empty wine bottle. And inspired by this, he drew an analogy to a baby trapped inside the birth canal. And by applying the same solution from the YouTube video, Odon has invented the Odon device and has gained the recognition of the World Health Organization. Surprisingly, despite the importance of analogies, few analogy resources exist today. We believe this lack of data hinders progress in computational analogy. Most resources mainly focus on word analogies, such as man to king is like woman to queen. We argue that this setting is too simplistic, often boiling down to a single relation. And in real-world, analogies are more complex, often involve multiple entities and intricate relations between them. Other types of resources do exist. For example, in the sentence-level analogies, there is a dataset of story pairs. However, the pairs are short snippets. In the paragraph-level analogies, there are few resources. Most notably are stories from cognitive psychology. However, these stories are manually curated and thus are very small. They also have near-identical structure. To bridge this gap, we leverage recent advances in large language models and develop a pipeline that generates much more complex and realistic analogies at scale. Our research realized in the seminal work of Gantner et al. And her structure mapping theory. According to her theory, analogy is a mapping from entities in the base to entities in the target, relying on relational similarity and not object attributes. For example, in the analogy between the electrical circuit and the water pump, there is a mapping between electrons and water and wire and pipe. A similar relation, for example, is that electrons move through the wire like water flows in pipes. But note that in terms of attributes, they are not necessarily similar. For example, the water is a liquid and electrons are not. In our work, we create a pipeline called ParallelPARC to scale up the process of generating analogies between paragraphs. In our pipeline, we use an LLM to generate analogy candidates. We use human annotators to label a random sample of the candidates and use these samples to train automatic labeling LLM. We propose two datasets, a gold set which is further validated by humans and a silver set which is automatically generated from our pipeline. In addition to the positives, which are the analogies, we use an LLM to also create challenging negatives, which we call our distractors. To demonstrate our pipeline, we create ParallelPARC, a dataset of paragraphs describing scientific processes across various domains. Here is an analogous sample from our dataset generated by our pipeline. It includes two domains, base and target, how does a solar panel work, and how does photosynthesis occur. Each process is described via a title, a domain, and a paragraph in a natural language. We also include the similar relations, hinting why the processes are analogous. Now let's dive into the different components in our pipeline. The first component is the generation of analogy candidates. The goal is to generate candidates from diverse scientific domains. How we do it? We employ GPT-3 as we found it produced high quality results at a very reasonable cost. We first tried a naive approach by asking GPT to generate two analogous processes without further instructions or constraints. But then we met two main problems. First, GPT tends to repeat itself. Second, GPT creates analogies of extremely similar topics. To solve the problem of repetitiveness, we seeded GPT with base instead of asking it to generate both base and target. To solve the problems of similar topics, we first tried to ask for target paragraphs in specific fields, but then often no analogies were found. Then we decided to select analogies in broad target domains such as engineering, natural, social, and biomedical science. This provided us a balance between diversity and specificity and also allowed us to control the distribution of the target domains. We first tried to use a single prompt for the task, but this led us to paragraphs that were mostly identical to the input paragraph except for nouns and also to artificially sounding sentences. To solve these issues, we used two separate prompts, the first for finding analogous subjects and similar relations, and the second to generate the paragraph in natural language given subject and relations. We decided also to include similar relations in addition to paragraph subjects and domains for explainability purposes. In total, we generate more than 4,000 of candidates. We now annotate a small portion of the candidate's data. The goals are to estimate the proportion of analogies and use the annotated data to train models. We hired Amazon Mechanical Turk workers. They received 2 paragraphs, base and target, corresponding subject, domains, and the similar relation. Their task is to decide whether the paragraphs are analogous and the similar relations are correct. If they choose yes, they need also to choose between close and far analogy. If they choose no, it means that there is an issue with the candidate and they mark it for further inspection with one of the following reasons: dissimilar relations, misinformation, cyclic versus non-cyclic process, or any other reason in free text. Based on the annotation, we estimate that the analogies are less than 30% of the candidate's data. We now use part of our annotated data as few-shot examples for our filtering model. The goal is twofold: to identify the most probable analogous candidates to show our annotators, and potentially replace the human in the loop and achieve a fully automated pipeline. This task is complex, and thus we use GPT-4. We input 30 randomly selected annotated candidates comprising 2 paragraphs, their subject, similar relation, and a label indicating how many workers label it as an analogy. Following the in-context learning phase, we run the model on our unlabeled analogy candidates. Our goal is to demonstrate how our pipeline can be used for creating datasets. We consider 2 types of datasets: the silver set, which is automatically labeled, and the gold set, which is validated by humans. We show our annotators both the most likely analogous candidate, as predicted by the filtering model, but also the least likely candidates. This allows us to evaluate the filtering model where it is most certain, and also balances the data for the annotators. We have 3 annotators per sample. To ensure high quality of our goal set, we choose a strict setting. A sample is positive if all 3 annotators agree it is analogy. We randomly gave annotators small batches till reaching more than 300 of positives. Annotators' agreement is around 80%, where random chance is 25%. Our goal now is to compare the filtering model's predictions to the workers' majority vote. Our model achieves an accuracy of 85% and F1 score of 83%. Importantly, it reaches around 80% precision, predicting high likelihood of an analogy, which is much higher than 30% base rate. In addition to the positive samples, which are the analogies, our aim is to create negatives. We can easily create simple negatives by using random target paragraphs, but those are quite easy to tell apart from analogies. Therefore, we now focus on creating the challenging negatives, which will be our distractors. Coming up with non-trivial negatives is a challenging task. Inspired by Gentner et al., our formulation is as follows. Let B and T be 2 analogous paragraphs. We create distractor T tag that keeps first-order relations as T, but changes the higher-order relations, means relations between first-order relations such as cause and effect or temporal dependencies. To create distractor, we find 2 dependent events in T such that one must precede the other and switch their order. Here is an example of the distractor creation process. On the left, we have a base paragraph about bats use echolocation. In the middle, we have the true analogous paragraphs about submarines use sonar. And on the right, we have the target distractor paragraph. As we can see, the events are reversed. On the distractor, we have that submarines first interpret the echo, and only then they emit the sound waves, altering the cause and effect from the true analogous paragraph. We use GPT-4 to generate distractors with 2 separate prompts. The first is a one-shot for finding and replacing 2 dependent events. We ask GPT to output a list of events in T according to their time, and then replace 2 dependent events along with an explanation. The second prompt is a few-shot for writing a coherent distractor. We ask GPT, given an order of events, to write a coherent paragraph. In terms of evaluation, a correct distractor should switch 2 dependent events with a paragraph that is coherent and consistent with the new order. We found out that GPT generates correct distractors around 90% of the time, and deduced that the distractor generation is effective and create for both the gold and the silver sets. In total, we have more than 300 of analogies in our gold set and more than 400 of analogies in our silver set, each paired with 1 simple and 1 challenging distractor. Note that this dataset is currently the largest of its kind and can be easily expanded with more API calls to LLMs. We then analyzed our goal set and found that we have a pretty balanced distribution between close and far analogies, and we found that the most dominant issue raised with the candidates is the dissimilar relations. We note that we also keep samples with annotator disagreements and issues identified by annotators for future research. In the second part of our work, we evaluate both humans and LLMs on propyrology benchmark of analogy recognition. We propose two tasks, binary classification and multiple choice, and evaluate both humans and LLMs in zero-shot and guided settings. Our research questions are as follows. What is the performance of humans and models? Is the automatically generated silver set useful for training models? And can the distractors fool humans and models? In the binary classification, given a pair of paragraphs, each describing a scientific process in natural language, the task is to decide whether the processes are analogous. The target paragraph could be a positive, which is an analogy, a simple negative, which is a random target paragraph, and a challenging negative, which is the distractor. In the multiple choice, given a base paragraph along with 4 candidate paragraphs, the task is to identify the paragraph that is most analogous to the base. We propose 2 setups. Basic, which includes 1 analogous paragraph and 3 random paragraphs, and Advanced, including the challenging distractors. Here are the results on the binary classification task evaluated on our goal set. We can see the overall and per target type accuracy of different state-of-the-art models and humans in zero-shot and guided settings. As we can see, GPT-4 achieves the best overall accuracy out of the models, and humans achieve better performance than models after a light supervision. The training of Flanty-5 Small on the automatically generated data significantly improved its performance. And lastly, the challenging distractors reduce the performance of both models and humans, and this result is statistically significant for models but not for humans. Here are the results on the multiple choice task evaluated again on our goal set. We show the results on the basic and the advanced setup, which includes the challenging distractors. As we can see, humans achieve better performance than models, and GPT-4 achieved the best results out of the models. Lastly, the challenging distractors reduce the performance of both models and humans, but this result again is statistically significant for models and not for humans. To conclude, analogy making is important for both humans and AI. We designed the pipeline ParallelPARC to scale up the process of generating more complex and realistic analogies. To demonstrate our pipeline, we developed propyrology, a dataset of analogies between scientific processes. In our experiments, we found that humans outperform models, and even the best model is more sensitive to distractors than humans. We also demonstrated that the automatically generated data is useful for training and improving models. We hope researchers will use our pipeline in domains where analogies have shown promise, and that this work will inspire more LNP works on analogies, leading to novel tasks and benchmarks. Here is our GitHub repo. See you in Mexico. Thank you.